Hello, my name is Stephen Hustedy. I am the principal developer of the Technology Academy at Guadalupe, or TAG for short. And I've been teaching computers and computer programming at South Mountain Community College since 1990. Now, if I do the math right, that is 35 years. When I taught my first programming class back in January of 1990, we were using IBM PCs with green text on a black background. They didn't do any graphics. Since that time, we've seen computers change a lot. They've become much more powerful, smaller, and much cheaper. Today, we have not only desktops, we have laptops, tablets, and smartphones that are extremely powerful and capable of displaying high-resolution images and full-frame video. I believe that someone who's trained in automotive technologies can troubleshoot their cars much better than us who are just typical drivers. They're better equipped to purchase the best vehicle, whether new or used, because they understand the inner workings and can therefore make better purchasing decisions. Well, I believe the same is true with computers. In this lesson, I'd like to introduce you briefly to what is under the hood, so to speak, and how computers work. We're going to get a bit technical, but I think it's helpful to realize that computers do not think, and they really only work on a binary system of high and low voltages, to which we ascribe the values of ones and zeros. Yes, we can think of everything the computer processes as either a 1 or a 0. Let's delve into that. We've seen previously that computers are digital electronic devices that take input from a user, process that input using programmed instructions, and provide output of the sought-after results. They can also store the raw inputted data, the results, and the programmed instructions for later use. The most common input devices are the keyboard and mouse, and the most common output device is the monitor or LCD display. In a desktop configuration, the central processing unit and the storage device, most commonly the hard drive, is within the box we might call the PC tower. These devices are connected by transmission channels, either physical cables or wireless connections. In an all-in-one computer, or a laptop, tablet, or smartphone, these separated functions may be physically in one device. Each device contains a motherboard. This is an electronic circuit board that provides for communication and connectivity between the functional parts. You might think of it as the traffic grid. The central processing unit, or CPU, is a chip that performs all the processing of the programmed instructions in accepting the input, manipulating it, and determining the results. It generates a lot of heat, so we see a fan attached here. As you can see, the CPU is not very big, but it can perform several billion calculations of the binary data every second. While computers don't actually think, we might, as an analogy, consider the CPU as the brain of the computer. Data and instructions are temporarily stored in the random access memory, or RAM. The RAM is also comprised of computer chips. The amount of RAM differs from computer to computer, but the more RAM, the more programs you can have active, and with more RAM, it'll often speed up the processing. There are many types of storage devices in today's computers. Historically, the most common has been the hard drive. While today most hard drives are solid-state electronics, until recently the hard drive contains some of the few moving parts inside the computer. They're sealed to keep out any dust particles, but inside there are hard metal platters with a magnetic coating and a movable arm that reads or writes data while the platters spin, kind of like an old phonograph. Another primary chip is the graphics processing unit, or GPU. Its job is to decode what color each pixel on the monitor should be and send that information to the monitor to display. Each dot of the monitor is called a pixel. And while monitors come in different resolutions, the most typical is 1,920 pixels wide and 1,080 pixels high. That's a little over 2 million pixels total, and each pixel takes 24 bits of information. We'll talk about bits and bytes in a minute, but that's almost 50 million pieces of data, and those 50 million bits are updated 30, even 60, and in some cases 120 times each second. Some computers use the CPU as the GPU as well, but a dedicated GPU is especially important when working with image and video processing tasks or playing high-resolution video games. We define the computer as a digital electronic device. And many electronic instruments are analog, meaning their voltage signals at any given moment can range from a high peak to a low value. But computers operate on digital communication basis. The signal looks like a square wave. where at any given time there's either a high voltage or no voltage. Let's explore that with a keyboard input. Let's say we're creating a letter to an old friend and we start with the word hello. When we hold down the Shift key and press the H key, we get a digital signal that represents the letter H. It's comprised of 8 bits of either high or no voltage. When we press the E key, we get a different digital signal. We press the L key, another different digital signal. But it's the same pattern when we press the L key a second time. And then finally, the O key. Just so we can see the pattern of high and low or no voltage is better, let me color code the signals. That makes it a little more obvious. But to make it even more distinguishable, let's assign a 1 to the high voltages and a 0 to the low or no voltages. It's easier for us as humans to work with patterns of 1s and 0s. And we can thus designate everything the computer understands as a 1 or a 0. For text, this really isn't so much different than the old West days of communicating by telegraph. The Morse code used in a telegraph communications was comprised of 2 values, a short dot and a long dash. This was an audio code that the telegraph operator on the receiving end would listen to and translate back into text. In our modern communications, we are concerned with uppercase and lowercase letters and all kinds of proper punctuation, so we need a larger base of those 2 values. Each character traditionally is represented with a combination of 8 binary 1s and 0s. You and I don't naturally think of a binary system when we think of numbering things. We think in a base 10 or decimal system. And we can convert the binary digits to a decimal digit. So we can say that a capital A has a decimal signature of 65, while an uppercase Z is 90. Each 1 or 0 is called a bit, and 8 of them together comprise a byte. The byte is the basic building block of computer data. When we talk about data storage or data capacity, we use terms like kilobyte, megabyte, gigabyte, and terabyte. Respectively, these are roughly 1,000, million, billion, and trillion bytes. There are 256 different combinations of zeros and ones in a byte. If every bit of a byte is 0, the decimal equivalent is 0. If every bit of a byte is 1, the decimal equivalent is 255. And with all the combinations in between of the zeros and the ones, we can say a byte can have a decimal equivalent value between 0 and 255. The output to the monitor display is also a binary digital signal. And each pixel of the monitor is made up of a combination of red, green, and blue light, whose channel is a byte and can be set at intensity values between 0 and 255. If all 3 are set to 0, we have black. And if all 3 are at full intensity, we have white. And in between, we have approximately 16.7 million different settings of color. This highlighted pixel has a tad more red light than green or blue. Let me demonstrate that with this little interactive program that I wrote. Here's a brief interactive demonstration of how those zeros and ones can represent the 16.7 million different colors with those 24 different ones and zeros. Think of a room where outside that room we have 3 sliders. Those sliders can be moved to a value between 0 and 255. We have a slider for a red light bulb, a slider for a green light bulb, and a slider for a blue light bulb. And when those light bulbs combine, we get different colors. When the sliders are all at 255, we have full intensity red, full intensity green, and full intensity blue, and our room over here on the right-hand side is filled with white light. However, if we move all those sliders down to 0, we've turned all the lights off, and the room, of course, is black. But we can bring just the red slider back up to 255, and we have a room filled with red light. Same way, if we just do the green slider all the way up and the other 2 all the way down, we get green light, and then finally blue light. But anywhere in between, we can do combinations. If those sliders are all at the same level, we'll get different levels of gray. And if we combine red and green at full intensity, we get yellow. Or green and blue, we get cyan. Or red and blue, we get magenta. And then there's all kinds of different combinations in between. And we can modify these sliders and make any one of the 16.7 million different shades of color. That's more than the human eye can actually distinguish between. And each one is represented by 24
ones and zeros were 3 bytes. 1 byte for red, 1 byte for green, 1 byte for blue. And guess how data is stored? It's the same system of zeros and ones. Now, on the older hard drives, data was stored magnetically by setting the poles of microscopic magnetic particles to either positive or negative. Today, we tend to use solid-state electronics rather than magnetic particles, but the system is still the same. It's just zeros and ones.
Well, that concludes our lesson. I hope you learned a few things about how computers work and maybe are inclined to delve a little bit more into what the different components are of a computer and what to look for in purchasing. We'll do a video later on how to make the smartest purchasing decisions for the system that best meets your need.